Welcome to video number 5 in Microfluidics. So in this lecture, we're going to continue to keep building on what we've been developing in the course. So we first looked at dimensional analysis, right? And then we took a set of the equations for fluids, showed how to derive them, and then we used that dimensional analysis to make a more simplified form of the equations that apply to microfluidics. Well, now, so I mentioned in the last lecture, we can then use that to get exact solutions. Well, now we're going to go ahead and look at those exact solutions. So we're getting really a complete picture here. Now we have the equations developed, and now let's go ahead and see how we can solve them and then get actual numbers, actual flow descriptions out of that. And so in this video, I'll solve section 4.1 here. And then in the next video, I'll do section 4.2, which will be the exact solution for the startup of a two-dimensional channel creeping flow situation. Okay, so I've realigned the slides here for this lecture, see if I can get some more space for writing. And again, just a reminder, like it's better if you take your own notes throughout this and don't just write what I write. So add on, as I go through the descriptions, make little notes for yourself. And that's the best way to make sure you retain and understand this information. So let's start by looking at that dimensionless Navier-Stokes equation. Okay, and I'll write that out here. Okay, now we mentioned how no analytical solution exists for the full Navier-Stokes, but then we saw what we can do is, if we consider only flows with very low Reynolds numbers, right, we end up with the Stokes equation, because if the Reynolds number is really low, it multiplies all these terms on the left, so we can just go ahead and get rid of those terms there. So we notice what has happened is, it'll be much easier to solve this because this right here, that nonlinear term made it really challenging to actually solve this thing. So now in this form, we can get analytical solutions. And these analytical solutions are important because they really tell us about the flow. So we get to see in the equation exactly what terms control the flow, and if we change something, how the other things will change. So these analytical solutions are quite important for deepening our understanding. So we end up with the Stokes equation. I'll write that out here, right, for small Reynolds numbers. And something else that's going to help us out here. So if we look at that picture on the right there, that was just like a microfluidic chip that I developed in the past. And it just emphasizes here the normal shape of a microfluidic channel. So what we end up having is that they have these high aspect ratios. So that's why the title here of our exact solution says high aspect ratio rectangular channels, meaning that actually the width is much greater than the height, which is common because of the way these channels are made. So I'll just draw that out here. And this is what we're going to be solving for. Okay, and the dimensions I'll show here, so we make sure that it's clear what we're talking about. So height is in the y direction. X is our flow direction, right? So I've shown it shortened here, but actually the channel keeps going. So flow is like in this direction here. And then this is our width dimension. This is our height dimension. And this is the length of the channel. And again, so I've just shown a small slice of it here, but in the L direction, that just keeps going. And that's the direction of the flow. Okay, so that's our high aspect ratio channel. And the geometry of that is also going to help us solve our equations here. And just a reminder too, because it's going to be important, we can see from the equation, right, that we have the pressure balancing off with our flow. So in this type of channel, what you normally do is you'd put something like a syringe pump or something like that. You'd have some way of changing the pressure. So the flow in the X direction then is sustained by a pressure gradient in the X direction. That's worth writing out. Make a note of that too here. I'll write it out as well. Okay, so I'm going to expand out this equation, right? So it's in this simplified compact form now. Let's expand it out, and then we're going to talk about each of the terms. And so remember, like, I'm solving this exact solution for the flow equations, right, in microfluidics. But actually, if you just follow with me here and make sure you're getting each of the steps, these tricks that we use, right, to go from our differential equation into a solution, they're applicable across a lot of fields, right? So there's a lot of tricks that we take here, tools, things that we do to this equation that are going to be applicable. So make sure you follow me through here because this is really important stuff when it comes to getting exact solutions from our differential equations. So write this out. Okay, so that's the X component of our viscous terms there. And this, of course, I'm writing it dimensionally, right? Again, so I had it non-dimensionally above, but I'm writing it dimensionally here. We know what the J and the K, so the Y and the Z terms would be, so I'll just put that out here. No need to write the whole thing out. We get the idea from looking at the X equation. I'll include that there, so for completeness. Now, I got a fresh page here. Based on what we know about the problem, we can go forward here with simplifying the equation that I just wrote. So just make some notes here on the things we can do. So the pressure drop we mentioned is only in the x direction. Okay, so what that means then is any of those pressure terms, those pressure change terms in the y and the z direction, they go to 0, so we can get rid of those. We're also going to look at those uz and uy terms. So we end up with unidirectional flow, right? So flow only in the x direction. And the main reason for that is because we have what we call boundedness, the boundedness condition, which really just means we wouldn't expect there to be flow in the y or z direction because of the walls. So because it's bounded, right? So we can't have flow through those walls. So we say, therefore, there's no flow in the y or the z direction for this flow. Okay, so we only have the x component of our velocity left. So let's write it here, what we end up with after making those simplifications. So we're just going to have dp dx, because pressure is only a function of the x coordinate now, so we can write those as d's. And we're going to have these terms here, the ones I actually wrote out from above. That is all that's remaining. Okay, now we mentioned we also use the Stokes equation alongside of our continuity equation. So let's take a look at if continuity can help us simplify this, which again, this is a trick we commonly employ. Okay, so let's write this out in expanded form here so we see exactly what's going on. Okay, now we have no flow in the z or the y direction, right? So we know that there can't be any change of our u velocity in the y direction with respect to y. I use a different color here. So we can get rid of this guy and this term here for the same reason, right? If there's no flow in the z direction, we definitely can't have a change in the z direction flow in the z direction, right? So those terms definitely are gone. Now that leaves us with, so therefore, that first term, now that has to be 0. Okay, now of course, if that is true, right? If we don't have any change in our velocity in the x direction with respect to x, we definitely don't have our second derivative as well, right? That one also has to equal 0. So that lets us simplify. So I'm going to go back and write on this equation like 2 lines above here. So that goes to 0, right, based on the continuity equation. And now we're just left with the following term below here. And I'll try to use different colors so it's not all the same so we can see. So I'm writing this just in a different color here so we can see the result of that simplification. Okay, now this pressure gradient here. So we're imposing this pressure gradient. And what we're going to do is we're going to assume it's constant. So nice constant linear pressure gradient. So we basically say this is linear and that makes it like this. And it's negative because the pressure is lower downstream, right? So based on the coordinates we lined up before, right? So as x gets larger, p gets smaller. So that's a negative on that gradient there. So it's negative delta p over L. Okay, gonna need another page here. Okay, now to final simplification here, what we're gonna do is we're gonna non-dimensionalize and we're gonna simplify to, so we don't have sort of one dominant length scale. So watch the trick that we do here. So we're gonna use h, the height, right? Therefore, if I scale y, right? So I end up with a dimensionless term there, but I'm also gonna scale z, and this is just about kind of like taking an extra step here. And then u will scale to some characteristic speed that's caused by the pressure drop, and that is worth writing. So I'll write this and hopefully you're still making your own notes as well. Characteristic speed related to the pressure drop, which drives the flow. Okay, so we look at this now, and now, okay, so the y1 is order 1, but this one is not order 1 because the z direction, right, you can go back and check the figure from before, that is our width direction, right? So, and our width, we said we're very high aspect ratio, so definitely, right, our width, our z coordinate there, the width can be quite a bit bigger than our h coordinate, right? So that's not an order 1 term. So let's keep this in mind as we write this. So I'm gonna simplify based on these non-dimensionalizations, and then we'll go ahead and see where that leads us. So negative delta p over L. Just going to write that out because we've seen this a few times now. Always helps for you to do it yourself too, so don't worry, there's going to be lots of practice questions for this kind of stuff in the assignments. Really, that's the heart of the learning for these grad courses, is like you kind of taking what we do here, doing it yourself in an assignment, and that cements the understanding, I find. Okay, I'll regroup all those guys over to the left here, so we end up with this. Okay, we can rescale this thing, right? Because we know that these characteristic values we choose, we can make that equal to 1. So we rescale this accordingly, and that gives us a hint at what our characteristic velocity should be. Okay, and then we'll have the following, right, once we do that. Okay, now, because we had that scaling earlier, right, when we non-dimensionalized up here, we're going to just do another term for this. We'll do this as like a z hat. Let's see if we can go ahead and scale this term now correctly, right, and see what happens. So let's introduce this scaling parameter to get us into the z hat mode, right, when we'll try to make that one an order 1 term. So we'll scale that with our dimensionless one from above. And let's just make a note, right? So this dude, we're aiming for that dude to be order 1, okay? Okay, and this epsilon to scale this is gonna have to be height over the width. So essentially we just switch, right? So we scaled it to h up here. I will circle that just so we're looking at it. So we scaled it to h here and said that's not correct though, right? So we don't want to scale the h, we want to scale the w, the width, and that gives us an order 1 term. So now let's just, to see where that came from, I'll give us a different color. So what do we have now? So the z prime, right, was z over h. Okay, so that means our z hat prime is like an h over a w times the z over the h. Z over w, so z over w, yes, that is order 1. Excellent. Okay, now all this to say, okay, so what did this get us? Alrighty, so I will substitute that in now to this equation, and again, we know how to make these non-dimensional substitutions, so let me go to a new page here. All right, so that equation then becomes, once we sub in for our epsilon one there, and you'll see in a second why we do it this way. You can shortcut this in the future, of course, but for now, I think I really want to demonstrate each of these steps here. So essentially, we have this epsilon term, right? And I'll just because I switched pages here, a reminder that that is our height over our width, okay? Now, we said that it's high aspect ratio, okay? So there's a simplification that comes with that, because if our heights, right, are a lot smaller than our widths, that makes this epsilon term very small. So I'll write that out here. Definitely pays off that I use these wider slides. So that is going to be much, much less than 1. And we know, right, that if that's really small, and what we have in our equation is actually epsilon squared is definitely also way less than 1, right? Way, way less than 1. Okay, so we know what happens, right, when we have these small terms multiplying out here. So that then goes to 0. Okay, and we're just left with this equation here. Oh, I haven't been putting primes on these, but that's, make sure you go ahead and add those in there. Like it's all dimensionless, so that should be okay. You should have recognized that. Alrighty, so that's gets boxed for completeness, right? We just say, so that's as our epsilon like approaches 0, it's really, really small. So a few things we note about this, right? So this has dramatically been simplified here, and all of these little sort of tricks and tools and tips we used along the way, those are really powerful, right? We see that our velocity in the x direction is actually only a function of y, okay? And actually this is similar to the Poisson flow through a duct, right? If you simplify for laminar flows. So I can make a note of that here as well. Hopefully you're doing this kind of stuff as well. So this is a function only of y. And what we've done here, right? So in simplifying this, we scaled our ux because we were looking for the dominant terms in this equation. So our strategy for this first part of the question was to say, how do we simplify this equation, right? And it was essentially saying, look, we have this geometry, we have these approximations, low Reynolds number, right? And we can get this in the simplest form possible before we try to solve it. That's what our goal has been up until now. So let's go back and redo this, right? Without the characteristic velocity, for example. And we're going to go back to our dimensional form. So I'll write this out dimensionally. Okay, so it would be like this. And now we're going to use a different non-dimensionalization. So we're going to use this here. We aim for some, like, usually average flow speed, right? So that's what capital U is here. Length scale. And then I actually need this X scaling just because of the pressure term there. Okay, so when I also go to scale my pressure, I'll scale it with the H as well. Okay, so what we end up with, I want to squeeze these next two lines here on this page. So we get, after these are subbed in, which again, we've done that a bunch of times. So I'll just write it out here. You'll get practice on your assignment. Okay, I remembered the prime that time. Okay, and then we see these cancel. And so we end up with the dimensionless equation like this. And now we use a trick. This is employed in fluid mechanics. We use this trick a number of different times. So we just kind of stop and look at this equation and we notice something that's interesting about it. So this side right here, that's a function of X. And this side right here, that is a function of Y. Okay. And so the only way those two things can be equal is if they don't actually have their X functionality or Y functionality, because there's no way to make them equal, right? If the left-hand side has X's in it, has X functionality, and the right side has Y functionality in it, there's no way they're equal. So they're only equal if it's a constant, right? So this, I'll write out here, is only possible if our pressure gradient, dimensionless pressure gradient, equals some constant. I'll do it as like negative kappa because that's the common notation. And this, just as a reminder, is a constant. All right, so now I need a fresh page, and now we can sort of start marching towards our solution here. So let's do that. Okay, so we have to write out our boundary conditions first. So we have Ux prime I've listed there. Let me just do a quick accompanying sketch here so we can see what's going on. So we remember dimensionally what we did above. So we put the origin in the middle there. X direction is our flow direction, right? Y is our height. So at a value of half there, right? Half of the height, just to make it clear, we'll say that's the wall. We don't have any velocity, so no slip condition, right? At the wall. And then because of symmetry at the center line, our symmetry gives us a nice condition here. So to make sure we have our symmetry, we say that that derivative is going to equal 0 along the midline there. And now we can solve. So solving for our vastly simplified equation here. Okay, so we solve this out, integrate our way down. For our constants, we go ahead and use our boundary conditions as usual. So this one, right, we can look to our middle equation there and see that means that C1 is 0. And our next at the walls there, we go down and solve. I'll use different colors here, like we plug in there. And that means that C2 has to equal this kappa over 8. And therefore, we have our solution, right? I'll write it in just a simplified form here. Okay, and that gets boxed. Now we sort of go further, right? So let's take that even further now. That, of course, is our solution. And what does this mean, right? Like, what does this actually look like? Let's keep going here. I don't think it's often enough that we do this. So I'll get a fresh page. Okay, now that U was our average flow speed, we know how to do these averages. From our channel geometry, we know the area, right? So we can get that our average speed then across the channel, sub this all in, I've gone ahead and done the simplification. So subbing in the W times H for area there in A, and you can make a little note of this if you want. That would have been WH, 1 over WH out in front of the integral, but then we have the dx integral as well, because dA is dx dy. So that would have multiplied everything by W, so the W's cancel. I'm just leaving that step out, and you can go ahead and make a note of that. If you like, now we want to do this dimensionlessly. And this, of course, is where having the actual velocity profile, right, helps us out, because now I just sub in here. We're calculating our average velocity, right? So I can go ahead and just plug it all in. I'll write it a little differently for the sake of making it clear what the integral is doing here. So that's what we have from above, right? Dimensionlessly. And then do the integration. I'll show the steps here on this one for completeness, from -1/2 to 1/2. And therefore, when we're using average velocity, our K or kappa, whatever you want to call it that we were using, is 12. When we sub all that in, that has to equal 12. Okay, fantastic. So now we can write this out in final form, just like that. Great, fantastic. And that can be boxed. That's our solution. Always make sure you box your solutions, right? And I'll put a few notes beside this here. Let's go with green. We're seeing a lot of blues today. A few things to note about this, right? So we look at this and we see that that is only a function of the y direction. Okay, so our velocity profile in the x direction only changes in the y direction. And then we'll note also, so this is actually a similarity solution, and it's valid for all flows through microchannels, right? So what we did here, we didn't do anything specific, right? So this is valid for all flows through microchannels, so long as the assumptions that we made are true, right? So I'll write that out, and our assumptions were low Reynolds number, high aspect ratios, okay? Okay, hopefully you can read that. Reynolds, much, much less than 1, and aspect ratio, H over W, much, much less than 1. That's the solution for all of our microchannels. Awesome. Really, really powerful, right? Okay, let's take this a little bit further. We're going to look at a solution now and talk about what this means for our solution. So use a fresh page here with our figure on it. Okay, so you can go ahead, we can go ahead and plot this out, right? So in this scale here, I'm going to put some labels on this. So this axis, that would be our y prime there. And in this direction, we're plotting u x prime. And that's what our profile looks like. And you'd have like channel walls would be like here and here. Okay, so that's our profile. Now the question is, what happens if our pressure gradient changes, right? So this is something that we'd like to know. Okay, so let's go back. And so what happens if we change our pressure gradient? Well, we can look at this to see, so our solution is still exactly the same, right? So our expression is still the same. It's only the scaling factor that will change. So let's take a look at this, right? So this was how we scaled this guy here. So what happens is, okay, so if this changes, right? If we change this term, then what happens here? Well, we can't change viscosity or height, of course. So what happens is u changes. Aha, you see, so our scaling was excellent. This we figured out, right, was that -12. So our capital U changes, average velocity changes, right? So the scaling still, the solution still looks the same, right? It's just that what we're scaling against, so our average velocity, capital U there, so that is what changes, right? Otherwise, it's the same solution. Okay, fantastic, which of course is intuitive. That makes sense. If I have more of a pressure gradient, I'm getting like a faster flow, right? Okay, second question, just to make sure we probe this, we really understand this. So what's the maximum speed and where does it occur? And we know, again, so we have the velocity profile. And once we have the velocity profile, we have an amazing amount of information. So we can go through this and say, if I want to know the maximum point, right, I take a derivative. And then I have from my expression above, I solve that. So it's -12 y prime. And then we say our maximum points, right, is when that's equal to 0. Okay, so therefore, right, that is equal to 0 when y prime is equal to 0, which we see from the plot, right? Y prime equals to 0. Let me get a different color. So at 0 there, right? That's our maximum velocity. That makes sense with that our solution there. And we get what is the value there? It's 3/2, right? And so that is a scaling, right? So we scaled that against the average velocity. So 3/2, and that's what that 1.5 there means. Okay, so we're 3/2 times our average velocity at the center line there. Again, intuitively, that makes sense for us. Okay, so that's it. That's what we got. So that's an exact solution to flow through microchannels. Awesome, right? And we can see, again, this process of simplifications are applicable to a lot of fields there. So just to summarize, right, we took our equations we had from before, simplified them with our dimensional analysis. We derived them in the last lecture. We ended up with our Stokes equation. And then we took our geometry of a microchannel. So flow in microfluidics occurs through these channels. And then we applied our boundary conditions, went through the whole solution, simplified our equation as much as we could, did a solution, and we got our final velocity profile for flows in microchannels. Okay, and that's all for video number 5. Thanks for watching.